This is Gergely checking in from Barcelona, and I'm presenting joint work here with Nikita Zhivotovskiy, who's at Google. And this paper is about how to obtain fast rates in the setting of online prediction if we allow the learner to abstain from prediction. All right, so let me just motivate this setting by the following very hard learning problem, in which the learner has to produce a sequence of 0-1 predictions under the 0-1 loss. All right, so in each round of this prediction game, the learner is presented an image, and then it has to say 0-1, which in this case corresponds to saying whether that's a dog or a mop on the picture. And every time you get it wrong, you pay me $1, otherwise you get to keep your money. Right, so you just keep receiving a sequence of images, you keep labeling them with zeros and ones. And as you can see, most of these images are rather reasonable. And after a bit of thinking, you can always say whether that's a dog or a mop on the picture. Well, except that there are some very hard images in this data set. And sometimes you just want to say, okay, I mean, I have no idea what is the right prediction here. I can really not make any confident predictions. So can I just, move on and forget that this has happened? Can I just abstain from making a prediction sometimes? So this is what motivates our setting to sort of try to understand when can we gain anything in an online prediction scenario by enabling the learner to abstain from prediction. How can we take advantage of this abstention option, and how much can we gain by doing this? All right, and of course, besides this contrived example, you can think of many more practical scenarios as well in which you can naturally define such an abstention option. For example, in the case of medical imaging, where you have to label a sequence of images corresponding to whether or not a person has cancer or no, sometimes it may make sense to just say that, okay, maybe it would be best not to rely on my machine learning algorithm to label this image and just defer to an expert just by letting the learning algorithm say, I don't know, I just want to have another expert opinion on this. And you can think of many and many other practical scenarios inspired by real life in which an abstention option can be naturally defined. But of course, we are here to study the theoretical framework. And as the foundation of our theoretical framework, we use this classic setting of online binary prediction with expert advice that we all know and love. So in this setting, we have to make a sequence of 0-1 valued predictions in a sequence of rounds T that goes from 1 to capital T. In each round, the learner observes the predictions of n experts. These predictions are 0-1 valued and are denoted as YTI for I going from 1 to capital N. And then based on these predictions, the learner has to produce its own prediction, which is also 0-1 valued and denoted as Y hat. And then after having made its prediction, the learner is also going to observe the true label, which is also 0-1 valued, and the learner suffers a loss afterwards, which is the classic 0-1 loss, 0 when the learner's label matches the true label, and 1 otherwise. All right, so this is a very, very classical setup. Everybody knows and loves this. So what we did here was extend this setup to allow the learner to abstain from prediction every now and then. So in our extension, the learner can produce either a 0-1 valued prediction or can just abstain from prediction, which just corresponds to producing an abstention symbol of star in each round. Right, and then the loss of the learner is still going to be the 0-1 loss whenever Y hat of T, the learner's prediction, is 0-1. And otherwise, if the learner decides to abstain, then it just pays this abstention cost denoted by C. So we make this assumption that C is bounded away from 1/2 in this entire paper, which can be easily justified by observing that it would be never worth it for the learner to use the abstention option if C was greater than 1/2. right? Because otherwise, the learner would be always better off just by flipping a coin that has an expected loss of 1/2. All right, so for the purpose of this talk, you should just think of C being equal to 0.49. It doesn't need to be very small, very close to 0 for any of our results to hold. All right, so this is the setup, and of course we consider the expected regret as our performance criterion. We are going to analyze algorithms from this perspective. The expected regret here is just defined in the usual way as just the gap between the cumulative loss of the learner and the cumulative loss of the best expert chosen in hindsight. Notably, the experts are not allowed to abstain still, so the experts still output 0 or 1 valued predictions, whereas the learner can produce zeros and ones or abstentions and is going to suffer this augmented 0/1 loss. All right, so it is well known that even in the case where the learner is not allowed to abstain, it is possible to guarantee a regret bound of square root of t log n for the learner for arbitrary sequences of predictions. All right, so this is well known. Here, t is the time horizon and n is the number of experts. And the question that we answer in this paper is, well, how much can we improve over this guarantee under the abstention model described in the previous slide? And turns out that we can massively improve over this existing worst case guarantee and achieve the following regret bound of log n over 1 minus 2c. So notably, this regret bound is absolutely independent of the number of rounds or the time horizon t, and it grows large as the abstention cost c approaches 1/2, right? Okay, so this is a so-called fast rate in online learning that we achieve here. So here's the algorithm that gives us this guarantee. It is based on the well-known multiplicative weights algorithm or exponential weights or hedge algorithm, if you like. This algorithm is based on maintaining a set of positive weights corresponding to the experts. These are denoted as WTI. These weights are updated in this multiplicative fashion. In each round, we just take our previous weight and then we just multiply it with e to the minus eta times the loss of the expert in that round, where eta is a positive learning rate parameter. And then having computed these weights, the exponential weights algorithm calculates an aggregated prediction based on the expert advice and the weights that were just calculated, right? So this PT is going to be a number between 0 and 1, which is just a weighted average of the expert's prediction according to our current weights, right? So the question is, having access to this aggregated prediction, how do we decide whether to abstain from prediction or to produce a 0/1 valued prediction? So I'm just going to show you some corner cases first that are going to justify our choice of abstention function. This is going to go as follows. Obviously, if p is either 0 or 1, we have no reason to doubt the output of our multiplicative weight algorithm. So we are definitely not going to abstain if p is 0 or 1. And otherwise, if p is 1/2, then we have no reason to lean towards predicting 0 or 1. We might as well just abstain in this case, right? Because by our assumption of c being bounded by 1/2, by abstention, we are always going to be better off by just not saying anything, right? So now we have established whether to abstain or not in these corner cases. And what we decided to do in this paper was just to linearly interpolate between these values and probabilistically decide whether to abstain or not. So what this graph shows here is the probability of abstention given this aggregated prediction PT. Right, and if we decide not to abstain and produce 0-1 prediction, then what we predict is the majority label, so to say, right? So if PT is closer to 1, then we are going to produce a prediction of 1. If PT is closer to 0, then we are going to predict 0 if we do not abstain. All right, so our main result is the following. If eta is small enough, which means that if eta half is bounded by 1 minus 2c, where c is the abstention cost, then this algorithm that I just explained has constant regret, has regret bounded by log n over eta. So naturally, this suggests that if c is far away enough from 1/2, then I should just crank up eta all the way to this value and just enjoy this regret guarantee. Otherwise, I can still recover the worst case regret guarantee. So this is summarized in this corollary, which is really our main result, that says that if c is bounded away from 1/2, then we get this log n over 1 minus 2c guarantee. All right, so let me just say a few words about the proof, really just a few words. So we just, our key argument is based on expressing the error probability of the base multiplicative weights algorithm, which is denoted as R, and then just expressing this so-called mixed loss in terms of this error probability R. It is well known that the cumulative mixed loss is bounded by the cumulative loss of the best expert plus the small overhead of log n over eta. This is a classic result that is to be found in every single analysis of the exponential weights algorithm. And then the second step in the proof is to show that the expected loss of our algorithm takes the following form. It is some function that is actually bounded, upper bounded by the mixed loss due to this expression that I'm showing on the left. Well, the trickiest part in the proof is really showing that this inequality indeed holds. For this, we just need to write both of these functions as a function of R and then just plot the functions, right? Well, of course, we have a rigorous proof where we quantify the condition of eta being small such that this guarantee holds. All right, so, but I'm just gonna refer to the paper on that one. We also have a lower bound in the paper that shows that no algorithm can do better than this. And this lower bound is based on a reduction to the statistical learning setting with the curved loss. We also have extensions of our changing abstention costs, where we show that if the costs satisfy a certain Tibakov style assumption about their concentration around the threshold 1/2, then we get rates that interpolate between the slow rate of square root of t log n and the fast rate of log n times a constant, where this alpha parameter really just describes the density of the abstention costs, empirical density of the abstention costs around 1/2. And we also have extensions to multi-class classification and infinite class of experts. So I'm also going to say that we are not the first to consider abstentions in an online learning scenario. There has been previous work by Corina Cortez, Maria Armori, Scott Yang, and Julia Dessau in 2018, who obtained slower rates of square root of t log n in a harder setting in which experts are also allowed to abstain, and the learner observes no feedback when deciding to abstain. And I'm also going to mention that this technique that we use for obtaining log n guarantees are very similar to the typical techniques that one can use to get fast rates for curved losses in an online learning setup. And I'm also going to mention that our setup is directly motivated by the very recent results of Olivier Bousquet and my co-author Nikita Zhivotovskiy, who showed that similar speed-ups can be achieved in the case of statistical learning by using techniques that are natively used for treating curved losses in that setting as well. So yeah, in summary, yeah, this was the first paper that we know about that shows that actually fast rates are possible in this online learning with abstention setup. Our rates blow up as C approaches 1/2, as expected. And of course, we have a bunch of open questions regarding whether or not such guarantees are achievable in other online learning settings where the learner is allowed to abstain. And we are really also wondering, what is it that really enables these type of guarantees? What sort of conditions can I put on my online learning algorithm or online learning setup that would enable similar fast rates? So with this, I'm going to thank you for your attention, and I'm happy to receive your questions, whatever form they are going to take.